the p-value of a statistical test. What is p-value? Assuming h naught is true, the probability that this test statistic will take on values as extreme as or more extreme than the observed test statistic computed from sample data is called the p-value of the test. The smaller the p-value computed from the sample data, the stronger the evidence against H naught. The p-value, sometimes called the probability of change, can be thought of as the probability that the results of a statistical experiment are due only to chance. The lower the p-value, greater the likelihood of obtaining the same or very similar results in a repetition of the statistical experiment. Okay? The point to remember is, smaller the p-value, stronger the evidence against H naught. Thus, a low p-value is a good indication that your results are not due to random chance alone. The p-value associated with the observed test statistic takes on different values depending on the alternate hypothesis and the type of test. Let's look at p-values and types of tests when the test involves the mean and standard normal distribution. In the example we just covered, example 2, we computed p-value for a left-tailed test. Left tail. Z of x bar represents the standardized sample test statistic for testing a mean mu using the standard normal distribution. Z bar is x bar minus mu over sigma over square root m. H naught is mu equals k. H1 is mu less than k. That's why we needed the left tail. The p-value is probability z less than x bar. This is the probability of getting a test statistic as low as or lower than zx bar. Here is the right tail test. Here H naught is mu equals k, H1 is mu greater than k. So you are going to find this area. What is Zx? Well, Zx is the standardized value. So probability Z greater than Zx, so you're looking for this area. What about two-tailed test? When is this applied? When the alternate hypothesis is mu not equal to. So not equal means you could be less than or greater than. That's why you are split between the two. Okay. So you're split equally between the two. So the p-value is split. Half of it here, half of it here. That's why p-value over 2, p-value over 2. So you're looking for probability z greater than absolute value zx. Multiply by 2 and that gets you the p-value. So you basically calculate the right hand side if you like and multiply by 2 to get the p-value. Types of errors. If we reject the null hypothesis when it is in fact true. So the null hypothesis was true, but we rejected it anyway. Then we have made an error. And that error is called type 1 error. On the other hand, if we accept the null hypothesis when it is in fact false, we have made an error. That is called type 2 error. So what is type 1 error? Type 1 error, null hypothesis is true, but we reject it. That is type 1 error. Null hypothesis is in fact true, but we did not reject H0. That is a correct decision. No error was made. What is type 2 error? Null hypothesis is false, but we did not reject it. That is type 2 error. Null hypothesis is false and we rejected it. That's a correct decision. There is no error. For tests of hypothesis to be well constructed, they must be designed to minimize possible errors of decision. Usually, we do not know if an error has been made, and therefore we can only talk about the probability of making an error. So we don't know the actual mu typically. So we are just talking about probability of making an error. Usually for a given sample size, an attempt to reduce the probability of one type of error results in an increase in the probability of the other type of error. So, understand, an attempt to reduce the probability of one type of error results in an increase in the probability of the other type of error. So this is interrelated, right? In practical applications, one type of error may be more serious than the other. In such a case, a careful attention is given to the more serious error. All right. If we increase the sample size, it is possible to reduce both types of errors. But increasing the sample size may not be possible. Good statistical practice requires that we announce in advance how much evidence against H0 will be required to reject H0. The probability with which we are willing to risk a type 1 error is called level of significance of a test. Okay? The level of significance is denoted by the Greek letter alpha. Okay, so that's A, but it should be alpha. So maybe we'll see there. That's alpha. Looks like A, but it is like that. Okay. The level of significance alpha is the probability of rejecting H0 when it is true. So H0 is true, but we still rejected it. So that is a type 1 error. So what's the probability of that happening? That's called level of significance. The probability of making a type 2 error is denoted by the Greek letter beta. What is type 2 error? H0 is false, but we did not reject it. Okay. Now, methods of hypothesis testing require us to choose alpha and beta values to be as small as possible. In elementary statistical applications, we usually choose alpha. First, the quantity 1 minus beta is called the power of a test and represents the probability of rejecting H0 when it is in fact false. Okay, power of a test. H0 is false and you manage to reject it. All right. For a given level of significance, how much power can we expect from a test? The actual value of the power is usually difficult and sometimes impossible to obtain, since it requires us to know the H1 distribution. However, we can make the following general comments. The power of a statistical test increases as the level of significance alpha increases. A test performed at alpha 0.05 level has more power than one performed at 0.01 level. Okay, so notice power of a statistical test increases. Power is 1 minus beta. That increases as alpha increases. So if you increase alpha, you have more power than the lower alpha. This means that the less stringent we make our significance level alpha, the more likely we will be to reject the null hypothesis when it is false. Using a larger value of alpha will increase the power, but it will also increase the probability of type 1 error. Despite this fact, most business executives, administrators, social scientists use small alpha. Okay? This choice reflects the conservative nature of administrators and scientists, who are usually more willing to make an error by failing to reject a claim than to make an error by accepting another claim. Okay? All right. Here is a summary. H naught is true. And if we accept H naught as true, this is a correct decision. Corresponding probability 1 minus alpha. H naught is true, but we reject H naught. This is called type 1 error. Its probability is called alpha, which is level of significance. Okay. If H naught is false and yet we accept it as true, then this is type 2 error. Its probability is beta. Suppose H naught is false and we reject H naught. This is a correct decision. The corresponding probability is 1 minus beta. It is called the power of the test. We'll come to this topic, next topic in your next slide. Until then.